talks about query to communication lifting for BPP and one Pseudorandomness level.
Okay, hello everybody. So my co-authors are the usual suspects for me, Tony and Tom. So I suppose this is relevant to the workshop because we are using some pseudo-randomness lemmas and properties in the proof, so you can start holding your breath. It will appear later on. But on a more higher level, what this talk is about relating query and communication complexities for a large class of Boolean functions. So we study both query complexity, so decision trees, and communication complexity, communication protocols. And I suppose for the two mathematicians in the audience, I have to recall what a decision tree is. It's a model to evaluate a Boolean function. So f is a Boolean function, takes n bits, spits out 1 bit. And it evaluates it by repeatedly querying individual input bits of the input until it finally knows enough about the input to output a value at a leaf of the tree. The complexity measure is the height of the tree, which is the number of queries you're making. On the other hand, we have a communication protocols that are a lot more powerful model of computation. Again, you're evaluating Boolean function. I call it capital F because now the function comes with a bipartition of its input bits into two parts, an Alice part X and a Bob part Y. And instead of querying individual input bits, you can evaluate whole arbitrary predicates of either the left side, the Alice side of the input, or the Bob side of the input. So of course we visualize this as Alice and Bob holding their inputs and they're having a discussion, sending bits to each other. So the cost here is, again, the height of the protocol tree, which is the number of bits that are communicated. And of course, these protocols are much more powerful than decision trees. I mean, if you have a decision tree for some function, you can convert it to a protocol of equal cost by just simulating an individual query by having the player that holds that bit communicate that value to the other guy. And they're strictly more powerful. It's easy to come up with functions that have low communication complexity but large query complexity. So the theme of this line of work that I'm going to talk about is to find general situations in which you could show that these two models are actually equally powerful. So a large class of functions where this would happen. This would be really nice for applications because you could analyze communication protocols by just analyzing these simple things, decision trees. So we'll be considering this large class of function called composed functions. So it starts out by just, you take your favorite Boolean function on n input bits. So these you study in query complexity. And then you turn it into a communication problem by composing it with a small two-party function. We call these gadgets. So it takes some bits from Alice, some bit from Bob, and produces 1 bit, which is then fed to the outer function f. So many functions in communication complexity, like set disjoint, is the most important function in this field. It's of this form. It's a big OR of a bunch of little AND gates that take 1 bit from each player. So more generally, you could consider then having this gadget be slightly a more complicated function. Maybe it takes m bits from both players, produces 1 bit for the outer function. So Alice's input then would be this mn bit binary string. So it's like you have n blocks, each of length m. And the intuition here is that if you choose this gadget as a complicated enough gadget, then the composed function should be hard to compute for protocols because you don't know what the inputs to the outer function are before you communicate enough information about the particular gadget. So if you want to know one of the inputs to F, you need to communicate stuff about the inputs to that gadget. So it's like you have to communicate bits to query an input to the outer function. So that's the intuition why we generally conjecture that for a carefully chosen gadget and for any outer function, the query and communication complexity should be related. So I call this the lifting theorem template. You can instantiate this sort of a claim for any type of computation you desire. So M here is a placeholder for, let's say, deterministic or non-deterministic model, which you can then further instantiate for either query or communication complexity. So I expect this to hold whenever you choose the gadget complicated to be a complicated enough one. And well, okay, there are a bunch of papers that have proved these sorts of theorems. There's one for deterministic thing that holds, non-deterministic, many models that are query complexity characterized in terms of polynomials. There are many such models. You can consider the exact degree, the approximate degree, or threshold degree, and so forth. But still, there's this one type of computation that's conspicuously missing, which is randomized models. And so that's what we're doing in this work. I suppose this was conjectured by a bunch of other people, so it's been really in the air. So what we show is that if you choose for your gadget this index gadget, so here Alice is holding this pointer, number from 1 up to n, and Bob is holding a string of m bits. The index gadget is just looking up in Bob's string the xth bit. So our main result is that if you choose this some polynomial-sized index gadget, well, maybe the constants aren't quite optimized, but if m is a polynomial in n, then we do get this characterization for the randomized communication complexity of the composed function. Maybe I should say that here Bob's input does blow up polynomially, but Alice is still holding these log n bit pointers, n of them, so Alice's input doesn't blow up too much. Well, nevertheless, maybe the input size blows up, but this is kind of the interesting scale of things happening. The complexity is characterized by the query complexity. Right, so I was inspired by this talk last week. We had this journalist in residence talked about history of the Silicon Valley and technological developments and their societal impacts. So that got me thinking, what are the societal impacts of a theorem like this? And I figured it out. So this kind of a thing, it puts people like me out of a job because it automates the task of proving lower bounds. So no longer can I write these kind of long technical looking papers that separate two models in an ad hoc fashion. We've certainly done this a lot. But now they kind of follow as a black box way from this. If you want to separate something from randomized communication, so just to spell this out, if you have some separation in query complexity against, again, some placeholder measure, large randomized query complexity plus low, whatever you're interested in, then you can just compose your witnessing function that exhibits a gap with the indexing function, and you get quantitatively, like up to log factors, a similar gap for communication. So here, just on the left-hand side, that's just saying that these two quantities are related by a logarithm. That's a theorem. On the right-hand side, it's always true that a protocol can simulate a decision tree. That's a trivial direction. So maybe you can imagine that now we can just go ham and derive all sorts of new applications. But it turns out that no, for the interesting reason that for any conceivable application of this, previously we have already went ahead and proved these things in an ad hoc fashion. So at the moment I can't say that any new interesting application would follow, but we do get simplified and unified proofs for previous results. So here's a sampling of something that we and other people have been doing recently, like separating classical from quantum in the communication world. So we had this Fox paper, for example, that proved a super quadratic gap for a total function between classical and quantum communication complexities. Kind of a horrible mess, but it was modeled on top of a previous query complexity separation. So this now also just follows directly from the query separation without ad hoc stuff. And maybe I should mention there's an interesting conjecture in query complexity about a particular concrete function. This is studied by Aronson and Ambine, some generalization of the correlation function, which if you could prove randomized query lower bounds for it, it would improve this gap from 2.5 to 3 in query complexity, and therefore by this new lifting theorem also for communication complexity in an ad hoc fashion, in a kind of direct fashion, whereas our previous methods, they don't imply it in a black box fashion. So at least there's a kind of a potential future application there. Okay, we can also do some exponential separations for partial functions and so forth. Okay, so let's maybe see a little bit about how this lifting theorem is proved. Of course, the non-trivial part, the theorem says there's an equality, but the lower bound is the interesting part. But depending on how you view it, it's a lower bound on communication or an upper bound on query complexity. And it's not even a huge joke, this, because you can phrase these proofs in two different ways. That's why we call this either lifting theorems or simulation theorems. Lifting is saying there's some maybe certificate of hardness in the query world. You can maybe construct a certificate of hardness for communication world. Many lifting theorems work like this. But I do prefer this more algorithmic way of thinking about it, of starting with a protocol and convert it into a decision tree of equal complexity. This is more algorithmic, but of course, these are just, we're just talking about the same thing in a different language. So I think my first point I want to make is that I want to reformulate this main theorem to kind of focus on what's essential. So I argue F is not essential. This holds for all F. So somehow the theorem is really about the gadgets, not about F. In fact, it would hold even if I put, instead of F, a search problem or something more general. So let's reformulate this problem. So here's the communication matrix of the composed function. So Alice is given again n copies of a pointer, and Bob has n tables, each of m bits. So this is the input domain of this problem. And so the first thing we do is we imagine partitioning the communication matrix into these what we call slices. So Z here was the input to the outer function, which is output of the n gadgets. So it kind of lives in this middle layer of this composed picture. So for each such thing, you can consider its slice. It's all the pre-images under the gadget, all x and y that map to it by the gadgets. So in particular, composed function would be constant on each of the slices. So this is an important notion. And here is the reformulation, the simplest algorithmic reformulation I can come up with. Of course, we want to simulate randomized protocols, but even simply, I can phrase this for deterministic protocols, we want to simulate the behavior of even a deterministic protocol randomly averaged over a slice. So the claim is that you fix any deterministic protocol, and I claim that I can come up with a randomized decision tree that it makes a number of queries proportional to the number of bits that the protocol communicates, and it outputs a transcript of the protocol. So the transcript is just a concatenation of all the messages that are sent. It's the log of the execution. So it's a randomized decision tree, so the output is some distribution of transcripts. And the claim is that that output is close in statistical distance to what the protocol would generate if you fed it a random input from the slice. Okay, so the decision tree has query access to Z, and it needs to produce this behavior of the protocol on a random input from that slice. So there's no A anywhere. This is really a claim about the gadgets alone. So let me spell out just why this implies the main theorem. We didn't really do much, we just switched our focus maybe. So to prove the main theorem, we want to translate a bounded error protocol into a bounded error decision tree. So here's my bold pi, it's a randomized protocol, and my decision tree is I fix its coins that yields a deterministic protocol. So I can apply the simulation, which produces a distribution over transcripts. And for such a transcript, I will just output the value of the leaf that is reached in that execution. Okay, I didn't really do much here. There are two random choices, the coins of the protocol and the random input from the slice. Two random choices, I can kind of swap random quantifiers. So nothing's really going on. But I just wanted to give this simple form to focus our attention. Okay, so let's look at what this goal we're trying to achieve, maybe what it looks like pictorially. So again, our goal. We fixed a deterministic protocol. This is communication 101. How do you visualize a deterministic protocol? My communication matrix is there, and maybe Alice communicates the first bit. And that induces some partition of the communication matrix along rows. Those rows where Alice sends a 0, those rows Alice sends a 1. So then Bob speaks, that induces a refinement of this partition into rectangles now along columns. So this continues, you run the protocol further, and the partitioning is refined at every step until we reach the leaves of the protocol. The leaves are in one-to-one correspondence with the rectangles in this final partition. So okay, this protocol is deterministic, it's a static partition. And only now I'm injecting randomness, this random point from a slice. This is what we're trying to simulate. The random point from a slice, it induces some distribution over leaves, or equivalently, distribution over walks down the protocol tree. And that's the object we're trying to simulate. So maybe I'll just rewind back to the very first message of the protocols. And how do we even simulate the very first message? We don't know which slice we're supposed to be simulating. We can only query bits of this Z if needed. But there's a very simple way to at least get started with the simulation, which is to kind of pretend that Alice is being given a uniform random input. And that would, in this case, picture, it seems like the first bit splits the whole communication matrix in proportions 2/3, 1/3. So our naive first step in a simulation is we need to generate this random walk down the protocol tree. So we just choose to go left with probability 2/3, right with probability 1/3. And this is kind of, so the kicker here is we prove a certain pseudo-random property of the gadgets that justifies us doing this, and it actually mandates that this is the only thing you can do. These are the only probabilities that make the simulation work. Okay, so this is the, we call it the uniform marginals lemma. It says that if you have a large enough rectangle in your communication matrix, large enough is defined in some technical manner, then this rectangle, it intersects all the slices, at least, but moreover, if you take any slice and consider its intersection with the large rectangle, imagine a uniform distribution there. Well, then the marginals of that distribution are close to uniform. So this kind of justifies this, our idea of just, if you're still maintaining a large rectangle in your simulation, then you just pretend that the marginal distributions for Alice and Bob are uniform, because really, no matter what the slice is, they're close to uniform. So at least first few bits that are sent either in our simulation or in the execution corresponding to a slice, they are close to each other. But of course, something interesting happens when we no longer have a large rectangle. So the technical condition here is such that for Bob set to be large, that's a condition that is always almost surely going to hold. So we're not going to worry too much about that. I mean, Bob's inputs are these very long tables of strings. We can really manage these sets to have, if you think of them as random variables, a huge mean entropy loss. But Alice holds these short pointers, so it's critical that there's some critical condition on what it means for Alice's set to be larger. We call it dense. It's this notion of blockwise density from a previous work. And so that condition says that, so boldface X here means, so Alice has a set, think of the uniform distribution on the set. And to me, it's blockwise dense is to say, consider any subset of these blocks, and 2 to the n choices, but for any subset, you can look at the marginal distribution on those blocks. And we just require that marginal distribution to have constant mean entropy rate. This would be the maximum mean entropy possible, but we say, okay, let's at least have 0.9 of that. So this is this notion of Alice having a dense set. And this is something that can fail, and it fails at some point in the simulation. So this is the part where we actually do something interesting. We start querying stuff. So when Alice's set loses density, our idea is just to restore it in the sense that we fix some of Alice's blocks in order to restore density on all the other blocks. So formally we compute this density restoring partition. Also we used this already in the previous work, where each of the parts in a partition is such that I've fixed some blocks in this Alice set in order to make the remaining blocks dense again. So here's like a picture of what's going on. Initially, all the pointers are very, very random, pointing all over the place in Bob's tables. But then we compute this partition, we pick a part in the partition to branch into with probability proportional to its size. It's kind of, again, this choice is justified by the uniform marginals lemma. But when you branch into one of these guys, it happens that we fix some blocks, maybe the first and the second block. So the pointers became fixed. They're pointing into fixed places in Pop's table. And so somehow we have to query the corresponding coordinates in this Z to figure out which slice are we simulating. And it typically happens that the places we're pointing to in Bob's table are kind of random enough that no matter what result we get out of these queries, we can then proceed to restrict Bob's set now into having these pointed to bits be consistent with this Z. So this is the first bit of Z, this is the second bit of Z. And this is basically what the simulation does. If you just ignore these blocks we fixed and made sure that the gadget outputs were consistent with Z, then what remains below is again dense. So that means that we can just continue the simulation pretending that the marginals are uniform. Okay, so basically the whole construction is trying to ensure that the resulting transcript is close to the one that would be generated if we had ran the protocol and random input from the slice. But then you have to separately argue that we don't query too many coordinates, which is related to the size of the subsets of blocks we're fixing. But okay, so that's kind of a sketch of the simulation, and I think I have to leave the technicalities for another time. So let me just, maybe it's been a long day, so we can relax with some open problems. I suppose that like with this randomized lifting theorem, the next obvious thing that's open is to try to prove a similar thing for quantum communication and query complexity. I should mention there's a recent paper that for the first time separated quantum communication complexity from approximate rank or logarithm of approximate rank. Approximate rank being previously our own only known lower bound technique for this model. So the analog of that was known to hold for query complexity for quite some time, but they now managed to prove it for communication complexity. If you had a lifting theorem for quantum protocols, then of course their result would have followed. So that's one motivation maybe to look for it. Well, another direction is that for many of the lifting theorems we have gadgets that they result in quite ugly functions, not really the natural things we would like we have in applications like set disjointness. So for those you would like to prove lifting theorems for constant size gadgets, and that's another direction which I think is very important. Okay, I do like to mention some challenges which aren't necessarily directly related to lifting theorems, but I'm being provocative here. Like maybe the most famous conjecture in communication complexity is this log rank conjecture that speculates whether the log of the rank of a Boolean matrix is polynomially related to the communication complexity of the underlying function. And so, again, like the query analog, it's known to be true, but we don't know whether the communication analog is true. So I almost hope that the conjecture is false in that that communication complexity is somehow richer than query complexity. That the whole subject is not just lifting theorem. But okay, who knows? Also, another problem I really like, but I suppose nobody really knows how to tackle it, are these age-old problems about proving lower bounds for models we have no explicit lower bounds for. Like what a lot of people have been doing recently is understanding models that have been already somewhat well understood, but even better. But these models we don't understand at all. So that would be most interesting. I mentioned here one recent work that pinpoints even weaker and weaker models of communication for which we don't know how to prove explicit lower bounds. And even formally you can show that our best methods fail to do so. So you should work on that. Okay, so I think I'll end here. Thank you.
So what property of the index function do you use?
Well, it's certainly a good extractor, as is inner product, which we used previously. I think what the index gadget buys us in just technical simplicity is that we just need to worry about Alice's sets being dense. So when that's like what determines what we're doing. And Bob said we don't really worry about it. It's allowed to lack a lot of entropy. So like one open problem is maybe to prove it for the inner product gadget, log n bit inner product for both players.
If you try the same simulation theorem, same simulation algorithm with inner product, what happens is like you fix one x, then say you're basically fixing an inner product for d-bit string. So you lose a lot of, there's only d bits and you lost one bit. And then you do this communication like n times, so you cannot repeat this. Whereas if you have indexing, which is m, which is like what, into the 10 or into the 100, at least in terms of counts, this can work. You fix one bit, but then there's maybe enough entropy to at least repeat this process.
One of your slides said something about approximate Nash equilibrium.
Right, yeah, so this is a paper, I think it's due to appear at Stock by Babichenko and Rubinstein. So they study a two-player game where the two players need to find an approximate Nash equilibrium by communicating with each other somehow. And the story with this paper is quite interesting. They first proved it for deterministic communication. It's hard to find an approximate Nash by a deterministic lifting theorem. And then we pointed out that you might be able to use these previous lifting theorems that stood for random. We didn't have the randomized lifting theorem back then, but they did some additional work, got it to work for randomized communication. And now with this one, you can again simplify the proof a little bit.
So the gadget there would be
I think it's kind of this complete problem of PPAD. Is this end of line type of problem?
They show a query lower bound. And then they lift it. It's technical.